Hello everyone, this is Dr. Young, and in this fifth part of our discussion about NMR, we're going to talk about the last major component that you want to look for when you're looking at an NMR spectrum, and that is the chemical shifts. So what are the chemical shifts, right? Remember that the chemical shifts are what tell us why does this triplet show up around a little over 1 versus this singlet is all the way at like 4.6, 4.7, and this quadruplet's closer to 3.5, 3.6. Why are they in different places, right? So before we talk about that, we need to get a little bit of terminology under our belt. So here is your scale, right? I have from 0 to 5 in this case. Oftentimes you can see NMR peaks up to maybe 12, 13, sometimes 14, depending on what the molecule is. But we don't see things at like 20 and 30 and 40 very often at all, not for normal molecules. In this case, it only goes up to 5, that's fine. We refer to moving towards the right-hand side of this spectrum as being what we call upfield. So I would say, for example, right, if I labeled these, say I call this signal A, B, and C, I would say that the most upfield signal is C. C is more upfield from B, B is more upfield from A. And then as you might guess, as I move to the left, that's called downfield. So as you move downfield, as the numbers increase, then you are more downfield. Associated with these terms are what we call the shielded and deshielded. So we can say that something's more shielded or something's more deshielded. As you move upfield, the idea is that the nuclei, in this case protons, are more shielded. So you get more shielded as you move to the right, and you get more deshielded as you move to the left. And we'll talk more about this idea of shielding in just one moment. So if I look at these, I could say, oh, well, apparently the nucleus that shows up in signal A is more deshielded from B. That's why it's downfield from B. All right, that's terminology we would use. Now, as far as this unit goes, ppm, parts per million, that comes from the fact that what we're measuring here is the frequency of the pulse used to tip the nuclei out of their field. And so what you end up getting, and this is, we're not going to get hardcore into this. This is not a spectroscopy class. This is not meant for spectroscopy classes or spectroscopy students. But let's say, for example, you are using a 300 megahertz instrument. That means that the field that you're in is 300 and then 10 to the 6, right? So 1, 2, 3, 4, 5, 6 hertz. But the pulse that you might use, the radio frequency that you might use might be 600 hertz, right, for a given signal. And so if you divide those out, you're going to get a really small number, right? So like 0.000002 in this case, right? Is that right? 1, 2, 3, 4, 5, 6. That's a really, really small number. But you'll notice that this is the same as 2 parts per million, because this is in the 1 millionth place, right? What's nice about using ppms is it doesn't matter what size magnet you use in your NMR spectroscopy or spectrometer. It's always going to give you the same ppms for a given compound, right? So if we use a 60 megahertz machine and someone else uses a 800 megahertz machine, we're going to get the same ppms. We'll have different line broadenings, but they'll show up in the same area of the spectrum. Now, so what is shielding, right? So I'm going to, again, this is very hand wavy. We're going to use kind of classical descriptions here, not quantum mechanical descriptions. But right, keep in mind that we said that these nuclei are experience a magnetic field, right? So here's again your magnet, your B0, your magnetic field. And so the nucleus here, right? The nucleus, this little blue dot is supposed to be the nucleus. Right? We know that protons are positive, so it's just a little positive thing right here in this hydrogen atom, right? And then it's surrounded by electrons. And I'm just going to draw an electron cloud around it that's pretty even, right? That's a nonpolar bond, a CH bond is not nonpolar. So it's surrounded by electrons. Now the idea is that this electron cloud is shielding the nucleus from the magnetic field. right? So when you have an H just attached to carbon, real nonpolar environment, it's got some electrons around it. And you can imagine different nuclei would have different amounts of electrons around them and different amounts of shielding, which is part of why we see like carbon-13 nuclei show up in a different place, different frequency than hydrogen nuclei would. Now, what happens here, if I look on the right, what I have here is I have a chlorine attached to this carbon, right? And we remember that chlorine, fluorine, bromine, nitrogen, oxygen, right? These are more electronegative elements, and so they pull electrons towards themselves. Now, what that's going to do is that's going to sort of deform this electron cloud, right? It's not going to, my electron's going to be pulled towards the chlorine. So now I don't have, right, again, if this is my nucleus here in the middle, I'm going to try to exaggerate this. I don't have as much electron density around the hydrogen that I used to, right? There's a less electron density because the chlorine pulled it away, because it's electronegative, right? That inductive effect. There's less electron density, and then therefore it is less shielded. It's less shielded, right? You don't have those electrons between the nucleus and the magnet, right? So it's less shielded from the magnet, which means, right, that this signal moves downfield. Let me clean this up, sorry. Right, so that means that I would expect that signal to be more downfield. It's going to have a higher ppm. It'll be more around like 3 or 4 as opposed to over by like around 1, 1.5, something like that. And so this idea of shielding and deshielding just has to do like literally with what is the electric environment around the proton you're looking at. So if you pull electron density away from something, it is less shielded. It experiences the magnetic field more. Now, we're not going to get hardcore into all of this, right? Again, this is just a OChem class. We're mostly learning how to try to read an NMR and predict what an NMR spectrum might look like. So the features that can de-shield a nucleus, right, are these things like electron withdrawing groups, like we said, right? We have O, N, F, a carbonyl, right? All of these things pull electrons towards a region, and in other words, away from the hydrogens that are attached near it. So that sort of basic inductive effect type thing, that de-shields a nucleus. What also de-shields a nucleus are pi bonds. So whether you're an alkyne or an aromatic ring or a pi bond, the movement of these electrons in these pi bonds creates its own little magnetic field that can interfere with the shielding and de-shielding of the nuclei around it. I don't care that we get hardcore into anisotropy. Again, that's more for a higher level class or a spectroscopy class, but you do want to know that, for example, the hydrogens that are in an aromatic ring get really de-shielded and move all the way down to like 6, 7, 8. Whereas in an alkene, they're kind of more around 6-ish, and in an alkyne, they're a little more upfield from that. So they have different shielding and de-shielding effects. You can look at examples in the book. What we want to know is, where do they show up? We want to be able to predict where these hydrogens will show up. Now, here is a table that I pulled offline from the online wiki, or from the LibreText stuff. And it tells you, right, if you have just a plain CH3 on an R group, just a plain alkane stuff, you tend to see that around 1, right? So 0.9 to 0.12. Versus if you have something around on an alkyne, that shows up more like 2.5 and 3. Or if it's on an alkene, that's more like 4.5, 6. And there are tables and tables and tables of these values. You can find them in your textbook. You can find them online. They can be very general, or they can be very specific, you know, breaking down every single possibility. By all means, you are welcome to memorize these lists. Go for it. You're welcome to use these lists for like homework and labs and stuff like that. But you also want to kind of internalize what these numbers mean and be able to predict products just using your big old brain. So I'm going to give you sort of a cheat sheet thing, kind of like I did for the IR, of like roughly where things show up. So here's a blank NMR, right? So I have 0 to 12. Again, that's where most things tend to show up. And we're going to chunk this out. So for example, between about 0 and 1.5. So note that this region here is about a 1.5 ppm range, about 1.5. So we're going from 0 to 1.5. These are your hydrogens on carbons that are just alkane-like. Right, so you're plain, boring Maybe it's propane, maybe it's cyclopentane, maybe you've got some highly branched whatever, just alkanes, nothing electronegative, no pi bonds, no, nothing very interesting, just alkane sp3 kind of boring stuff. That's where you'd expect to see those hydrogens. Now, if we get a little bit more interesting, the next group over here, so we're from about 1.5 to 3, these are hydrogens on carbons that are either attached to a carbonyl, or in other words, they're alpha to it, or these are hydrogens attached to a carbon that is right next to an alkene, or in other words, vanilla or allylic. Right? Allylic means one away from an alkene. Vanillic means attached to an alkene. So these are hydrogens on carbons that are then attached to a pi bond thing. So whether it's alpha or it's allylic. So like, for example, and again, this is a 1.5, right? About 1.5 range. So for example, that would be this friend, right? This carbon right here has hydrogens, and right next to it, right? This has hydrogens, and right next to it is a carbonyl. So I'd expect these to show up somewhere between 3 to 1.5 ppms. That's what we're talking about. Same thing over here. This carbon right here, same thing. It's got hydrogens on it, and attached to it, one away, is the double bond, right? So that would also show up in this, roughly 3 to 1.5 ppm range. That's what we're talking about. Not on the alkene, not on the carbonyl, one away from it. The next range is also roughly about 1.5. We're trying to keep this kind of consistent so that it's useful for you and your brain. These are the hydrogens attached to carbons that are then attached to something electronegative, whether it's a halogen, oxygen, nitrogen, etc., right? So chlorine, fluorine, bromine, something electronegative, something that's going to withdraw electrons. That's the friends that we're talking about here. So that would be something like this carbon, right? This carbon has hydrogens on it, and it's attached to a chlorine. So I'd expect that to show up somewhere between 4.5 to 3 ppms in an NMR. If I was to look at that, that signal should show up. That's where that signal should show up. The next group, so about 4.5 to 6.5. So now we are roughly about, this next segment is about 2. So right, the first three were all like the first 1.5, the next 1.5, the next 1.5. Now we're going 2 ppm, so 4.5 to 6.5. Now we are talking about the hydrogens on an alkene, the ones that are directly attached, right? So that would be like these suckers, right? So now we're talking about the ones directly on that. That should show up somewhere between 6.5 to 4.5 or so. That's where I'd expect those. So, and as far as the terms go, right, these are the vinyl or vanillic. I'll put vanillic. The vinyl or the vanillic hydrogens, the ones that are directly attached to the alkene itself, not one away. Next, we have a very important group that's really useful if you see this. So this is also a chunk around 2-ish, 2 ppms. So this is about 6.5 to 8.5. These are hydrogens that are on an aromatic ring, that are on a benzene ring or some other aromatic compound. So that would be like, for example, all of these suckers, right, should show up somewhere between 8.5 and 6.5. That's the rough area that they show up. I'll mention this more later, but these are looking at where things show up if they only have that feature, if they're only on a double bond, or if they're only attached to an oxygen. But if you're attached to a double bond and you're attached to an oxygen, that's 2 deshielding effects. So you're going to move further downfield, for example. So, right, if you're both vanillic and you have an O attached to you, you're saying, well, it's somewhere here, but it's actually going to be further downfield because I'm also attached to an O. So we'll see that these can kind of add up and stack also. And then the last area is going to be pretty much anything above 8.5 has got to be either an aldehyde or a carboxylic acid. Carboxylic acids tend to go higher. They can go up to like 12-ish. Aldehydes tend to be more like 9, 10, somewhere in there. Again, kind of depends on what your structure is. So somewhere in there. A little side note that I want to put on here, because you're going to see these a lot, is that OH groups, they can show up almost anywhere. So you're just going to look for some like singlet OH peak somewhere, almost anywhere. They can be around 1, they can be up near 9, 10 if they're on like a phenol or something like that, if they're on an aromatic ring. They can show up almost anywhere. So there's not really a good region to say that they're from. But OHs are common enough that I need to say this. So if you can memorize this like cheat sheet here of roughly where these things show up, you are going to be in great shape. You're going to be in good condition. You'll be able to look at NMR and get a rough idea about what you think that structure should be. And you'll be also be able to kind of predict where you think things should be. So I highly recommend that you internalize this. This will be great to use on tests and quests and stuff like that. So using that, the idea is that I should be able to come over here to these molecules and kind of predict roughly what ppms I should be looking for when I'm looking for this signal. So I'm just going to circle these here first real quick. It looks like I have 3 signals for this one. I'll start with the aldehyde. I just said, right, that aldehydes tend to be pretty high. So I'm expecting this to show up somewhere, you know, like above 8.5, maybe to like 10.5, something like that. Something above 8.5 is the idea. Something really high, around 8, higher than that. This group right here, these are CHs that I note are next to a C double bond O. And we just said that that range was between 1.5 to 3 ppm. So that's kind of where I would expect that 2H quintet to show up, right? Because it's got 3 neighbors to the left and 1 to the right, the aldehydes on an adjacent carbon. And then similarly, right, my aldehyde, I expect that to be a 1H peak, and that should be a triplet because it's got 2 neighbors on the next one. And then lastly, my blue signal, right, I expect that to be a 3H peak that is a triplet because it has only 2 neighbors. But that's kind of alkane-like, right? It's only attached to a CH2, so it's not really very interesting. So it should be somewhere between 0 to 1.5. Maybe a little on the higher end because that carbonyl is near-ish, but somewhere in the alkane-like region. That's what I'd expect. If I did a similar thing for these over on the right-hand side, same idea here, right? I'd expect these to show up, right? They're vinyl, they're on the alkene. This should be somewhere between 4.5 to 6.5. The ones right next to it are the allylic ones. Those should be somewhere between 1.5 and 3. The one next to that is pretty boring and alkane-like. That's probably between, 0 and a 1.5. And then lastly, this one right here is attached to a chlorine, which is electronegative. So I'm expecting somewhere between 3 to 4.5 parts per million. Right, so using that little cheat sheet thing I showed you in the previous slide, you should be able to kind of predict where things probably are likely to show up. We can also go backwards here, right? I can look at an NMR and start to say, I wonder what might this be attached to? So like if I look at these 2 peaks, they're between 6.5 and 8.5, which I said was the aromatic region. So I know that these hydrogens are attached to an aromatic ring. And so that's when I build the molecule, I'm going to draw an aromatic ring and try to put these hydrogens and these chemical signals all together. When I look at this next one at about 3.6 or so, I notice that that's in the 3 to 4.5 region, which means that this is a hydrogen on a carbon that's attached to something electronegative. Again, whether it's an O or an N or some sort of halogen or something like that, I'm not sure. I don't know what the formula is. I don't have a mass spec. I can't really predict that. But I know that it's attached to something electronegative. That's why it shows up in that region. If I take a look at the next one, that's in the 3 to 1.5 region. That's telling me that this signal is a hydrogen on a carbon, and that carbon is either double bonded to an O or that hydrogen is on a carbon that's double bonded to a C. I'm guessing right now that there's a good chance that it's double bonded to a C because there's a whole bunch of CC double bonds in an aromatic ring. So maybe this group is coming off that aromatic ring, which is why it's near a CC double bond. But I'm not sure yet, right? I don't have enough information to put it all together. And then lastly, if I look at the one on the far right, this triplet out here, it's between 1.5 and 0, which means this is a hydrogen on a carbon that's just alkane-like. It's just kind of plain boring sp3s, Cs and Hs. So that'd be the most shielded one, right? So again, the terminologies, this is the most shielded signal. This is the most de-shielded signal. This one's the most upfield. This is the most downfield. Right, so we should be able to predict forwards and backwards kind of what these structural things are. What we're going to do in another video is kind of do a whole bunch of examples and kind of put this all together. How would we decide what the molecule is if I have some information like IR and a formula and stuff like that? Lastly, real quick, we're back to this sucker, right? So if I call these, remember that we'll call this A, B, and C, and I think I said that the integrals for this were 3H, 2H, and 3H. We knocked this out because it has the wrong number of signals. We knocked this out because it had the wrong integrations from the previous videos. That left the first and the third one. The first and the third one have the right splitting patterns, right? Like if I take a look at this signal versus that signal versus that signal, we said that this was a 3H singlet. We said that this was a 2H quartet, and we said that this was a 3H triplet, right? That was from previous videos. Now we can make predictions about where we think they should show up, right? If I look at the blue one, the 3H singlet, that is one away from a carbonyl. That means its peak should show up somewhere between 1 to 3 ppms. That's what we said those show up, those alpha hydrogens. Now, do I see a 3H singlet at between 1 and 3? No, I don't. I do not see a 3H singlet between 1 and 3. My 3H singlet is all the way up at 3.5. That's not a good sign. That means that might not be this. Let's look at the other ones, though. If I look at the 2H here, so I have the 2H quartet, that is attached to an oxygen, so I'm expecting that one to show up between 3 to 4.5 ppm. Do I see a 2H quartet all the way up there? No, my 2H quartet is like at 2.4. It's not above, sorry, I don't know why that disappeared. 3 to 4.5. It's not above 3, right? That singlet's above 3, so that doesn't seem great. And then lastly, if I look at my 3H triplet, that's alkane-like. I expect that to be somewhere between 0 and 1.5 ppms. Again, I don't see that. That's not what I see. Right? I see actually that one is okay. That one is okay, right? I have a 3H triplet that is at like 1.2, so that jives. That's the only one that really matches. Let's take a look at the other possibilities, see if it's better or worse. So again, I'll circle that one, and this one, and this one. So again, 3H, it looks like it's a triplet. It's got 2 neighbors. Again, it's alkane-like, so it should show up between 0 and 1.5. And it does. That looks good. For my red one, that is a 2H peak. It has 3 neighbors, so it's a quartet. That is attached to a carbonyl, so I expect that to be between 1.5 to 3 ppm. If I look up at my NMR, well, sure enough, look, it's between 1.5 and 3. It's right at 2.2. That looks good. And if I take a look at this one, right, we said this is a 3H singlet that has no neighbors. It's attached to an O, which should put it somewhere between 3 and 4.5, because it's attached to a really electronegative element. And sure enough, my 3H singlet is between 3 and 4.5. So that means that this friend is the molecule that best correlates to that NMR. That's how we put all of these pieces together. I know it's a lot. With practice, it all starts to click and go together, but that's what we want to do. So speaking of practice, I'm going to make another video where we just practice and look at like 4 or 5 different spectra and kind of interpret them and see if we can get all of these 4 factors, the signals, the integrations, the splitting patterns, and the chemical shifts to all make sense and tell us what a structure is.